traveling.
And my stomach.
You have a traveling in.
Yes, and orange juice.
Why don't you just share that?
Judging so.
Nobody asked.
Do their actions show some regulars?
So you said you were in the physics lab party?
I get,
It's a boat.
one of them riddle me this.
Actually, it's a logic.
I
can't wait tomorrow too.
So I just slept till like 8:30 and realized, wait, it's 8:30.
Oh, why does it look like Mars?
No,
It looks like Mars.
I could not medically act.
What is that exactly?
Things
I
like
could call
Tim
her
Dix.
mom.
No
I
problem.
Yeah, I just didn't know.
That was
Then how is it chocolate? It's just like fruit.
Yeah, exactly.
The vanilla one's
It's a
so
smoothie.
Yeah.
It's like calories.
Yeah.
This makes me want to hug my mother.
Alright.
Not do that anyway.
No. Has to be a special occasion. No, family comes first. True apples. That big cheesy concert. Big Sean, dog.
Big Sean. Anytime anyone talks about Big Teddy,
Huh?
no one is going to see Big Sean.
I'm going to see
What?
Big Sean.
I'm going to see Big Sean. Not Kid Cudi, Big Sean or Logic. No, it's Kid Cudi's just there. Nobody would have come without Big Sean. You going to a concert? Where you at?
I don't know. My friend has all her tickets.
But
Really
yeah.
irresponsible.
Not going to the concert?
Yeah.
Where you going?
The MIP, I'm pretty sure.
Do you know where you said?
You don't want to know.
Nice.
I got the meeting.
My friend got ground tickets, full tickets.
Dude.
It's gonna get close enough. I mean, I'm not against them doing this, but we went to the Wiz last year, and we just talked.
61 pages.
Oh, they're gonna see me after
That's
that.
good.
I'm kind of.
No, we were still. If they turn out well, I still ever see. Yeah.
If I smile,
Some
they're
chance.
Close your eyes.
Where?
I'm not too sure. I don't think you read out to this with Kelly.
Don't say Snoop Dogg. Snoop Lion.
Change your name whenever you want.
Yeah, you can. Bob
Oh,
Marley
that's
did
great.
it.
Completely different animal.
The Bobby
Let's see.
C.
Queen,
Yeah,
Prince did it.
Snoop Dogg.
Quadrupeds.
Okay, time to start. Considered in itself, the will that departs from reason is always bad, no matter whether it is right or wrong. In other words, always doing the right thing is good, but doing the right thing for the right reason is best. Okay, let's go back to the Atwood machine. So, given that we have gravity and these two masses hung on this pulley, and that the pulley is massless, and it spins without friction, that's not really, so it spins without friction. I don't mean that the rope slides without friction. I mean that the pulley spins without friction. And also the rope is massless and stretchless. Then you are to find, in this problem, the accelerations of both masses, the tension in the rope, and a third item is the weight of the machine. In other words, there's a rope that holds it up to the ceiling, and there's some force being exerted on that rope. What is the force that is being exerted on that rope? If you were to hold the machine up, how much force would you have to exert to hold it up? It's not equal to the sum of the two weights of the masses. It isn't. So let's go through this, and then I'll ask somebody, hopefully somebody has thought about why that last fact that I gave you is correct. But let's go through this. We started this last time, and I want to finish it today. What's the first step? Mr. Averett, for problems, general solution to motion problems, what's the first step here after writing the diagram?
You want to put force diagrams.
Force diagrams. Didn't I mark that in your paper?
Yeah.
Force diagram. So we want what forces are acting on this first mass. You want to start me off with this one?
Oh, you got the force of G.
Okay.
Mg. And then you got the tension force.
Good. And how about the second one?
You got that second Mg.
Okay.
And then you got that also tension force.
And it's the same tension. Can you give me a reason why the tension is the same?
Because the rope is the same. The rope is not stretching.
And also that the pulley is massless. We'll find out when we consider in Chapter 7, Chapter 7, the rotation of rigid bodies like pulleys. Once we consider the rotation of a massive body, that the tension will not be the same on both sides. So the fact that it's massless, or in other words, that it's much less mass than either of the bodies that are hanging there, that'll get the same answer there. We can neglect the mass of the pulley. So, okay, Ms. Swanson, what's the next thing I do?
Pick a coordinate system.
Good. Yeah, I've written over the area here where I would have wanted to pick. Can I do this? No. How do I do that? I did it by accident somehow one day. I got this whole thing to slide over. It must be, there we go. I wonder if there's some way I can grab it all. Hey, I'm learning here. Okay, cool. There we go. Now I can draw a coordinate system. What coordinate system would you pick for this problem?
Well, I would just pick a standard one. Like, I've done some problems before where they turn it on its side, but I guess that would, then that'd be implying, friction or something like that. But, they turn the whole diagram on its side, if that makes sense.
Not in this case. I wouldn't see how that would make sense in this case, right? Yeah.
But, I guess just a standard one, because there's not,
This is not good here. This thing is blinking, isn't it? Oh, my goodness. Okay, that's because they were fiddling with things here. They were trying to fix it. They really fixed it. I'm sorry. Go ahead. What would you pick?
Y positive would be, pointing upwards, and Y negative would be downwards.
Okay, so would you pick the same Y coordinate system for both masses?
No, because, wouldn't it be a positive force in one direction and a negative force in another?
So you would choose to, that Y for one of them is going up and Y for the Y2 is going down, which is fine. Okay, so that's one possibility. So let me try to diagram that for you. So in this case, we would have a marker here and say, going up this way is Y1, and going down this way is Y2. Right? That's one way to do it. And that's fine. Mr. Kelly, would that one have occurred to you? Would you pick a different one?
I would have just made it Y upwards and just made one of them
Okay.
positive.
Choosing Kelly Green here. There is another choice would be to do both of them up.
You just keep the magnitudes the same, but you can change the signs to indicate direction.
Right. Either is fine. Either way works. But you got to pick one, and there are probably other ways you could invent here to do this. I suppose you could mark both of them going down from the ceiling. That would be another choice. Okay, lots of choices. I don't care what you pick. Just be clear about what you pick. You'll find out with experience some are better than others, and so Ms. Swanson is anticipating here that we're going to apply the constraint of having the rope of fixed length, and that the if her y1 is positive, y2 will also be positive. And so she's chosen a system in which all the displacements will be of the same sign. They'll either both be positive or both negative. Whereas Mr. Kelly's goes the opposite way. Y1 is going up, and y2 may be decreasing. Okay. So, I've forgotten, what does he do in the book? Does anybody remember? He chooses a coordinate system in the book. I don't remember. I thought maybe somebody would say, oh yeah, I just read that.
I think he does both of them going up, and then he says that the accelerations are negative.
He's chosen for them both to go up. So he's used the Kelly-Green method here. And so let's use that one. Let's use what we did in the book. What's done in the book. So I'm going to, for clarity, stop. Okay. For clarity, I'm going to erase this first quite reasonable choice of coordinates. I'm just going to choose that one for definiteness. Okay. And now, what's the next step? Mr. Sharp, what's the next step here after we've written the force diagram, chosen a coordinate system?
I'm not sure, to be honest.
Okay. Who would like to help Mr. Sharp? Ms. Maw.
You resolve the forces onto the coordinate system?
Okay. Right. And so how do we, in this case, that's really pretty simple, isn't it?
I mean, we sort of just did that a second ago.
Yeah, it's really simple here, right? Because the tension is positive and the weight, the gravity, is acting downward in the negative y direction. So that's really simple, right? That step. Okay. So what's next, Mr. Fanning? After we've discussed that the T's are positive and the G's are negative, going downward, so what's next?
Write the equation for the net forces.
Good. Equations of motion in particular, right? Newton's second law. So how do we write Newton's second law for this mass M1? So it's going to...
Tension plus minus M gravity.
Which one, M1, M2?
M1.
Okay, good. And what does this equal?
0.
Is it 0? That would imply it's not accelerating. If these masses are not the same, will this thing accelerate?
Yes.
Yes. Okay, so they're not equal to 0, and in fact that just gave you an idea here. It's accelerating, so this is going to be related to the acceleration of which body?
M1.
Yes, sir. So I could write it as M1 A1, where A1 is equal to Y1 double dot. Okay. Now how about the equation of motion for the second mass? Keep going.
That's T minus M2G.
Good.
And that's equal to M2A2.
Good. All right. And so now what we have yet to put in the fact that the rope is present, except that by virtue of the tension. But we haven't. There's something more that the rope does in terms of the accelerations of these masses. Ms. Shaban, how would I express the fact that there's a rope present here that has some effect on these masses? In what way? I'm looking for a third equation here that expresses the presence of that rope in terms of these two accelerations, A1 and A2.
No idea.
Are these two accelerations related to each other?
Yes.
And in what way?
Inverse.
Yes, right. Inversely meaning they're negative of each other, right? Not reciprocal, but inverse in that sense. And the sign there, notice that A1 is the negative of A2, comes about because we've chosen both, when both are positive acceleration, they're both up, and so one of them has to be accelerating down. If one is accelerating up, the other is accelerating down. So some of the signs in this, if I had chosen the other coordinate system, the one that Ms. Swanson suggested at the beginning, these equations would look a little different. The signs would be different, right? So maybe after this we'll go and try the other coordinate system, see how it works out. But this is specific to having chosen the coordinate system the way we did. And this is the way it's in the book. Okay, so this first one is Newton's second law for the first mass. The second was Newton's second law for the second mass. And this third equation has to do with the rope has fixed length. It's stretchless. And that means that the two masses have to accelerate in concert in some way to reflect the fact that they're connected by that rope. Okay, so what's the next step? Mr. Disharoon, do you remember what the next step is?
Identify unknowns.
Yes, okay, so what are the knowns and what are the unknowns here in this set of three equations? So unknowns, and what are the knowns?
No gravity.
Yeah, you know G.
I guess we know how M1 and M2 compare to each other.
Yeah, you know M1 and you know M2. Those are given when I stated the problem. I drew the original figure and I told you what they were. So what is left there? We have three things that are left.
Tension, acceleration.
The tension and the two accelerations. Right. So are those unknowns? Yeah. You don't really know what the tension is until the only way to find the tension is through solving these system of equations. So I have three equations, three unknowns. And they're all linear. This is straightforward algebra. So I would like for you at the moment, I'll give you about 2 minutes. All right, 3. I want you to find T, A1, and A2 from these three equations. This is a simple problem in algebra. Three linear equations, three unknowns. I want you to solve for T, A1, and A2 in terms of M1, M2, and G. They're in the book. You could certainly look up the solutions, but I'm not interested in that. I want to make sure that everybody knows how to do this algebra with facility. I think that was about 3 minutes. You need to practice this. If you did not finish in that time, you need to practice this. It's going to be on the test. I want you to derive it. At least something very close to this will be on the test. Not exactly this, because this would be too easy. If you practiced it, you just regurgitate what you've done. But you should be able to take a system of 3 unknowns, 3 linear equations, and find each of the 3 unknowns. Okay? So practice that, get it down fast. Speed is part of the advantage of knowing this stuff, is you can do certain things quickly and with confidence and without mistake. Okay, the solutions are in the book. Okay, now let's do a dimensional analysis on these to make sure that they're correct. We have an acceleration here, which is the difference in masses divided by the sum of the masses and then multiplied by an acceleration. Okay, so the ratio of 2 masses is dimensionless. So this is really easy to see that this is dimensionally correct. Acceleration is proportional to an acceleration. And the other acceleration is of the opposite sign, so that's good. How about this one here? We have product of 2 masses divided by the sum of masses, so we have a mass squared divided by a mass. So the dimensionality of this tension is going to be a mass squared over a mass times an acceleration, which is, oops, I should write that as a dimensionality. An acceleration, which is length per time squared. And so this is a mass length per time squared. Is that the correct dimensionality for tension? What is tension in the rope in terms? It's a force. Does it have the correct dimensionality for a force? Yeah. Okay, so you could check a few limits here. Does it make sense that if m1 equals m2, the accelerations both go to 0? Does that make sense? All right, so we did a dimensional analysis check. Also, let's do common sense. Remember, extra credit for these things at the bottom of your homework or test problems. If you find these solutions and then apply dimensional analysis and common sense checks, I will give you extra credit. So what if m1 equals m2? What should the accelerations be?
0.
Right. They're balanced, right? There's nothing that will... Does it mean that the machine is not moving? No. They're not accelerating, right? They could be moving. The point is they're not accelerating in their motion. So if you put them still and let go, then they'll stay still. But it doesn't mean that they're not moving. So if the masses are balanced, the accelerations are 0. And how about the tension in the rope? If the masses are the same, m1 plus m2 in the bottom gives 2 times the mass. And so we get that the tension is just equal to mg, just equal to the weight of 1. Does that make sense? If m1 equals m2 equals m, let's call it. Let's go back up to our force diagram up here, over here, and see, in fact, if they're not accelerating, then the tension has to balance the weight for each one, right? And that does make sense. The tension in that special case. Okay. Here's, all right. So, is there another, that's an easy one to do, set the same masses. Another case might be, let's try another case. What if one mass is much greater than the other mass? It's got a tiny BB with this great big, massive weight on the other end, right? How is that going to move? It'll certainly accelerate. What will be the acceleration of, well, they're both the same acceleration, right? One is positive, the other is negative, but they're the same magnitude. What will it accelerate with? What will be the magnitude of the acceleration?
About G.
Yes, sir. Good, Mr. Vestal. Why? Why do you figure that?
Because if you plug in
Don't plug it in the equation. That's
Okay.
correct. I want you to apply your common sense first, and then let's see if the equation follows that. Does
Okay,
your common sense tell you that that should be G?
Well, also, yes.
Good. Let's start with that.
There's going to be basically no no resisting force from the baby on the massive object.
A BB's just not going to have much effect. Right. And so if you just take this great big massive object and let go with this tiny little BB attached to it, it's just going to fall, accelerate with acceleration G. Okay, so in that case, one would expect the acceleration, first one would accelerate up, and so it should be G. The BB should accelerate up, and the bigger mass should be downward with negative G. Okay, good. How about the tension in the rope? And this actually answers the first question in the homework. Let's go back to the force diagram of the BB. This is the BB here. Let's look at the force diagram of the BB. And we said that this thing should accelerate upward with acceleration G. So what does the tension have to be?
Almost nothing.
Not almost nothing, because if it's almost nothing, it's going to fall. It's going to accelerate downward. The tension has to be not almost nothing.
MG.
Not, if it's mg, then it will balance and it won't accelerate at all. Keep going, one more. Add another one.
Halfway between.
Halfway between, that would be 0. Oh no, it would be halfway between 0 and 1. I guess, no, that's not going to work either.
Wait, what's going on? What we trying to do?
Okay, I want to find out what t has to be in order to make the BB accelerate upward, right? If t is 0, it accelerates downward. But we just found because it's attached to this great big mass with this rope that it's. Well, it's not negative. It's definitely got to be up.
Has to be about G.
If it's m1g, it balances the weight and it doesn't accelerate at all. It's got to be greater. How much greater?
The proportionality between
Any amount greater.
Not any amount. It's a very specific amount. It accelerates with g up.
Twice.
That's what I meant by.
There it is, twice. 2m1g. I'm sorry?
By negative, I meant like in the
Oh my
opposite
gosh.
direction of where it would normally be.
Ah, okay. But would that be m1g? Okay. So there's a net m1g force acting up that makes it accelerate upward with g because it has mass m1. Okay, let's check our formulas to see if that works in that limit. If we set m2 is much greater than, let's go back here, so a1 is equal to m2 minus m1 over m2 plus m1 g. And what if m2 is much greater than m1? Like m2 is 1,000 and m1 is 1. It would be 99 over 1,001 times g. And let's keep on making the difference even bigger. So let's make it 1,000,000 to 1. So it's now 999,999 divided by 1,000,001. It's getting closer and closer to 1, right? So in that limit, this becomes approximately equal to g, which agrees with what we thought should be the case. And how about a2 will be the opposite. So that's m1 minus m2 over m1 plus m2. Well, that's just a negative, so it's. And let's check the tension. T times T is m1 m2 times 2 over m1 plus m2, all times g. Okay, so in the denominator we have the m1 plus m2, and the m1 is really small compared to m2. m2 is just huge number. m1 is small. So in the denominator, we could just replace it by m1. We can neglect the replace it by m2. We can neglect the m1. So this is approximately equal to 2m1 m2 over m2. And the m2's cancel, and so we have this approximately equal to 2m1g, which is what we said we should be getting, right? That makes sense. Now, the tension in the rope is twice the weight of the lighter mass. Kind of interesting. Not much tension. We got this great big massive thing that's accelerating, and the rope doesn't have much tension in it because it only has to lift the BB, right? It's hardly doing anything to this big mass. It's just got to accelerate the BB. which doesn't take much. Okay, so good. We've done a common sense check. Everything looks good. And we have answered 2 of the questions. Found the accelerations, found the tension in the rope. We also did the dimensional analysis and common sense check. Everything looks good. How about that last thing, the weight of the machine? How much force is this machine applying to the ceiling? We have this rope here at the top. Let me draw it in thicker here. There's tension in that rope, too. How much tension in that rope? Let's call it T prime. Ms. Shaven's got it. 4T. Anybody agree with that one? Why 4T?
Because each one has 2T.
Oh, each one has 2T? Wait a minute here. Let's go back here. I think you might want to change your answer.
No, I don't. I want to argue it.
All right. T that way, right? T this way. Okay. How much does the rope pull down on the pulley? T here, T here. Does the pulley accelerate? No. Pulley doesn't accelerate. So those 2T. But there is a 4.
I know.
There is a 4. So T prime, the weight of the whole machine, T prime, the weight of the whole machine is 2T. And remember, T has already a factor of 2 in it, so there is a factor of 4. That's what you were remembering, right? Maybe. Maybe. Okay, so the weight. So let's do the common sense check again for the weight. Remember, when the masses were the same, so common sense. Special case, M1 equals M2 equals M. The weight of the whole machine here is 2m squared over 2m. I'm sorry, 4m squared over 2m. G, which is 2mg. The whole thing, when the weights are balanced, the whole thing weighs the total weight of the 2 masses that are hung from the pulley. Does that make sense? They're just hanging there. So that makes sense. Okay, so it's not accelerating.
No.
Now let's try making one much greater than the other one. What is the weight of this machine? Well, let's do the same thing here. 4 times M1, M2, and M1 plus M2. If M2 is really big, this is going to be down in the denominator here is going to be M2G. So this is approximately equal to 4 times the weight of the BB. Not the weight of the BB, not the weight of the bigger mass, but the 4 times the weight of the BB. Kind of surprising result. But if you think about it again, what is the tension in that rope? Well, it's got to be twice the weight of the BB because it's got to accelerate the BB upward. And those 2 tensions at the top here have to balance the tension in that top rope. So therefore, it's got to be 4 times the weight of the BB. Now, I would love to be able to do this demonstration, and I challenged our demonstration people, and Mr. Hester and Ms. Brandenburg, to come up with a demo to demonstrate this last year. And they came up with something. It was a little bit challenging, though. You can understand the challenge here. If M2 is much greater than M1, then it's going to be accelerating with G, right? So you got to set up this apparatus and then let go, because this is only going to be happening when it's accelerating. So you got to let go, and it's going to accelerate, which means it's going to fall. And you got it in that, you know, if the apparatus has that far to fall, what does it take? A second or 2? You don't have long to make the measurement of the weight of the apparatus. All right, so it wasn't real convincing. They came in, they gave a good try, and it worked pretty well. Actually, the weight, the measurement was off a little bit. It didn't turn out to be quite what we were predicting, and I think that was because of a lot of things. You know, it was on a pole, so it was wobbling like this, and then the whole thing is accelerating, and it only got 1 second to make the measurement. And
Measurement as in time?
yeah. Well, you can only measure it while it's accelerating, and that doesn't last long.
What are they measuring?
Measuring the weight of the whole apparatus. So what they did was they put a pole where they put this pulley system hanging it on, and the pole was on a scale.
Oh, okay.
That's one way to do it. The other way to do it is to hang it and use the scale up there. Either way should give the same answer.
So you got to look at the thing in like a heartbeat.
Yeah, about between two heartbeats. That's right. Boom, boom, and that.
Use like the spring sounds.
Well, okay. Here's my challenge. I don't want to discuss it here in class right now, but here's a challenge. I'd like somebody to come up with a better demonstration of this, because I'd really love to do this for my freshman class.
Oh, we're not freshmen anymore? You're just going to get rid of us like that?
I'm not. You're going to be always having successors, right? There's always somebody after you.
So just.
I know that
just
breaks your
about
heart,
now.
but there's always somebody after you.
Okay.
God bless. So, get together, think about it. It'd be nice that maybe we have to do this outside. Maybe we have to do this from the ceiling from the roof of Kynard, right? And the thing has to accelerate 4 floors. That gives us more time.
Can we get an A if we do it?
Yeah,
Can I get
I'll
an
give
A?
you an A. I'll write it down for you. And
Can I get like a freshman to 50? Like if I do this right?
I'll give you a Z if you like. What? I'm sorry, what did you say? All right, so anyway, there's the challenge. It would be interesting. I'd really like to have a better demonstration than what we have on hand right now. And it may take a little bit of thought. This is not really that difficult, and it may involve, so you could ask Mr. Hester if he has some equipment that you might need. Do you know Kristen Brandenburg? Have you all met her yet?
Oh, I met her.
She's junior, I think.
Yeah, she was junior in celebration.
So she's an undergraduate physics major. She knows what I'm talking about because she tried this. She knows the challenge here, so she'll know when you tell her that I sent you to her, she'll know why. Okay. All right. So let's see here. So going back for a minute here to the question of the assumptions that we put here. Massless pulley, we will go back and consider the effects of a massive pulley in Chapter 7 when we do rotating rigid bodies. So we'll come back to the Atwood machine again, and we'll do the accelerations now where the pulley itself cannot be considered massless. It'll be interesting to see how that changes. The stretchless rope, of course, what would you do? Well, you might consider a rope that has some stretch to it, a bungee cord. And so that we could start doing in Chapter 6 when we do the springy systems. We're going to have springs. And so we could say we got a spring instead of a rope. What would happen if we had a spring? We could start doing that one. The massless rope, you actually considered some of the effect of that in number 35 on the homework today, which is what happens if the rope is not massless? Well, we have to consider the acceleration of the pieces of the rope, because the rope is accelerating and it requires forces present on it. So the tension is not going to be the same all along the rope anymore. The tension is going to be distributed along the length of the rope in a non-uniform way. The tension is not uniform. Okay, and that's revealed by the solution of the problem that I'm not going to go over. You can read the solution here. But that's how you would have to try to modify this if you don't have a massless rope, or if you don't have a massless pulley, or if you don't have a stretchless rope. You've got to start changing things here. You've got to start putting more in. So this is, again, the idea of abstraction. We can isolate these things in the mind, whereas in the physical reality it might be challenging, not impossible, to minimize these other effects. Okay, so you have for next class, for Friday, let me do it for Friday, you're beginning Chapter 5. So reading for Chapter 5. As before, you're going to, don't put away your papers yet. You're going to need your paper. You're going to need some blank paper here in a second. Reading for Chapter 5. So that's what, today is the 9th, so that's October 11th. And then for Friday, October 18th, there's an in-class test. Chapters 1 through 4. So as usual, we're starting Chapter 5, and I'll give you a couple of days to digest Chapter 4. I'll grade your homeworks, get them back to you. You can study solutions. Then we're going to have a test on Chapters 1 through 4 in class a week from Friday. Okay. And right now, at the moment, we have enough time for you to take a pop quiz. So take out one blank sheet of paper. And you have until the end of the class, which gives you about 10, 11 minutes. There's 7 rather brief questions. Some of you may finish before the end of class, in which case feel free to leave. Number 6 on this quiz is not a yes or no question. You could say yes or no, but I'm not going to give you full credit unless you explain your answer. Okay, explain that. And I'm adding a question to this quiz. It's a very fresh quiz. Number 8 is up here on the screen.